Okay, let's get started with trigonometry. Before we do that, is there anybody here with their name up on the board here? Kate, I need you to do your test at some point. We need to come up so come see me at Focus so we can have a chat about when that's going to happen, right? Okay, trig review. How many people know or remember a little bit about what we did for trig last year?
Not a thing.
Not a thing? That's not good.
That's a hard reality.
It's fair. That's fine.
Sine,
Sine, cosine, and tan.
I know what that means. I don't know how to do it. And then you can do negative sine, cosine, and tan.
Okay, we've got sine, -1, cos, -1, and tan, -1. When we were using these units or these terms, what were we trying to find? There was two things we were trying to find. An angle or a side. Awesome. And when we're talking about a side and an angle, what shape are we talking about? Okay. We start with a triangle. Okay. And we started building not just, and I believe when we started this, we had a little piece on how actually trigonometry should be called circleometry because it was built around that idea of the sun and the rotations around the 8 different angles. Okay, it ends up building a triangle based on that. Okay, we had certain side lengths that were specific to us. What were they? 90 degree. Yeah. Yeah, what were they? Adjacent, where, and hypotenuse, and what's the last one? The opposite. Where do we find those? If this is my...
Hypotenuse is the side across from the 90 degree.
Say it again?
The hypotenuse is the side across from the 90 degree.
So it's opposite of the 90 degree. It's also the very longest side, okay? Typically that happens when it's a 90 degree. The side that is opposite the 90 degree is your hypotenuse or the longest side. Who can tell me the big difference between the opposite side and the adjacent side?
Opposite is opposite of the angle.
Opposite of the angle. So if I'm given an angle, which is symbol is theta, if I'm given the side or the angle, I'm looking at this side as being the opposite. It's always opposite the side of given. The adjacent process of elimination is always in between the angle I'm given and the right angle of the 90 degrees. We're all good with that? Okay, we had different methods of algebraically solving those pieces depending on whether we were solving for an angle or solving for a side, yes? Each one of these trig law or terms had a formula attached to it. Sine was equal to opposite over hypotenuse. Cosine was adjacent over hypotenuse, and tangent was opposite over adjacent. Take a lot of those concepts, throw them out the window.
No.
Okay? We are going to come to situations where they're going to be beneficial to you, specifically with regards to if I give you a triangle or I give you a situation where you have to use some different problem solving or it's a secondary skill. However, we're going to actually look at back to coordinate grids or Cartesian planes. We're also going to talk about different angles. We're also going to talk about how to solve. This is a right angle triangle, yes? Okay, we actually evolved this into what happens when we have a triangle that looks like this. What's the big difference? I mean, don't mind my drawing that it's not as accurate, but what is missing compared to the last triangle? We don't have a 90 degree angle. So you could, but if I don't give you that line in the middle, you don't quite know. Let's say I don't draw it to scale, and I just give you some scenarios. You don't quite know what that number is in the middle, right? So, and that's a strategy that could work, Andrew, for sure, but I'll show you how to solve this without having to do that. Okay? That's when we get into some trigonometry with regards to solving for area, solving for sides, what have you. Okay? Today, it's as an introduction to trigonometry, we're actually going to talk about the unit circle. Remember we talked about how trigonometry should have been called circleometry? first introduced trigonometry, I gave you the circle off a Cartesian plane or the coordinate grids. Okay? We're actually going to break down, we're going to dissect how we come across and actually build an angle that looks like this. Remember if we had the sine 1 opposite, you could actually figure this is how it was brought up into play, how trigonometry was brought in because of the angles in which the sun was rotating. Okay, we're actually going to break that down to start, and then we're going to evolve it into solving for triangles. Okay? So the first example, we've got a coordinate grid. Within that coordinate grid, we have 4 subsections, 4 sections. Everybody sees those 4 sections so far? Yes, no? We actually split this up into 4 quadrants, okay? Each quadrant has a different role, and each quadrant has a different percent or angle section within it, okay? We call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay? Within each quadrant, we can actually label what our x and y values are, and this could be a little bit of a review so you understand how we're getting through. If I have an x and y value, any x and y value, as an ordered pair, what are the values, what are the symbols that you will see? What is the x value always going to be in quadrant 1? Always going to be positive. Okay? My minimum value is what? 0, and then it can go on positive forever. If my y value is in quadrant 1, what value or what sign or what symbol is my y value? Positive. Okay? Keep those in mind because when we start talking about the unit circle, when we start breaking down different ratios, you want to be able to understand where these x and y values are and what symbol or what sign they have. Now let's look quadrant 2. Quadrant 2, what's my x value have to be? Negative, and my y value has to be? Okay. Third, quadrant 3. X value has to be? Y value has to be? Alright, and then the last one, x is? Positive. Y is negative. I'm just going to write the letter y. Y is y. Alright. So we've broken it down into 4 quadrants. We actually use this with regard to really break down how we see angles. And with regards to circlometry, we actually use the quadrants to split up 360 degrees into 4 subsections. Okay? When I first introduced trigonometry to you last year, I gave you a drawing that, I'm actually going to clone this page. I'm going to clear ink. Okay? When I gave you this page, or this concept, I gave you an example that looked like this. And I said, alright, the sun at this certain point is at this certain length from the origin. Okay? This is what we call standard form of an angle, given in a quadrant, in a Cartesian or coordinate grid. Okay? We have 2 terms here that I've highlighted. One's called the initial arm, one's called the terminal arm. The initial arm, if I split this in half, or in a, I guess, 360 degrees, where do you think I would put 0 degrees with regards to this coordinate grid? Anybody have a thought of where they would put 0? On the x-axis. Now would you put it to the left side, or would you put it to the right side? I'd probably put it on the right as well. Okay? So we're starting at 0 degrees. 0 degrees is to the right of the coordinate grid. This is actually where your initial arm is. Okay? Are we starting to see a little bit of a triangle shape here? Okay? This becomes our initial arm. Why do you think it's called the initial arm? It's like our starting point. Okay? We always start at 0 degrees. And when we're talking about angles in standard form, we always start at 0 degrees, and the hinge is always at the origin or right in the middle. Okay? Where the second line, or where the angle or the destination is, that's actually called our terminal arm. And that's the length in which we are traveling. Okay? You may see what angle we potentially could be measuring. What angle could you measure here?
Between the terminal.
Good. That's the guy we're looking for. When we're given an angle in standard form, using our coordinate grids, we're looking for the angle in between the initial arm and the terminal arm. Okay. Questions on that so far? All good? Standard position. We've got two little groups here, and I found a visual that hopefully will give us a good understanding of what they're asking, or what the difference is between standard position and not standard position. All these sections in Group A, these three examples in Group A. What the key points here are, we have our initial arm in each one, and we have our terminal arm. Where is that hinge at? Always at which part? 0 or the origin. Okay, 0, 0, the origin. It's always in the middle. Each one of these has a hinge at 0, and the initial arm is the same as our x-axis. Okay, what's the problem with the first one in Group B? Other than a lot. What specifically? Jared, what's one thing that's wrong with it? It's not at 0. What part? The origin or the hinge. The hinge is not at 0. What's another thing that's wrong with it? Really, the big thing is that hinge is here. Where should it be? Down and over. Okay? What about the next one? What's wrong with, so the hinge is not, so this is an issue. What's the issue with the second one? Anybody? The initial arm, where is the initial arm supposed to be lined up at? It should be at 0. Is it right now? No, our initial arm is not parallel to anything, or in line with the x-axis. Okay? What about the last one? Is the hinge at 0? Is my initial arm at the x-axis? So neither of those. So we have this guy here, and we've got the initial arm at, who knows where, it's on an angle again. Okay? Big thing with standard position. Your initial arm is on line with the x-axis, and your hinge is at 0, 0. Do you guys need to write that down, or are we good with that so far? We're good? Do you want me to write it down?
Yes.
Sure. Okay. Hinge has to equal 0, 0. Which is also the origin. Okay, and the initial arm has to be equal to the positive x-axis. Does that make sense if I write it like that? Just because it's on the x-axis doesn't mean that it's still in standard position. The hinge has to be at 0, 0, and the initial arm has to be on the positive side of the x-axis. That good? Okay? Would you like to move on? Let's go to the next part here. Now, which of these three, I want to see all hands, A, B, or C, shows, which diagram shows an angle of 70 degrees in standard position? When you think you know which one it is, I want you to put your hand up. I'm not moving on until all hands are up. Okay? So if you're not quite sure, I want you to think about it, or ask a friend if you're not quite sure where it is. Okay? But here's where I want you guys to be thinking about what's happening and what the justification could be. So not just, so specifically, tell me which one is in standard position and tell me why the other two aren't. Okay? Alright, Taylor, because you're the only one that stuck it out, put your hand up. What one is in standard position? B. How do you know the other two are not? A is not on the origin. Okay, so the hinge, not at origin. And C, not on positive x-axis. Has to be B, at 70 degrees. Very good. Okay. Before we continue, I want to talk about this just before we go any further. We talked about, I've used the term 360 degrees. Why am I using 360 degrees? Where do we compare that to? The circle, back to circleometry, right? So we said, we agreed that 0 degrees is at the initial, or the starting point on the right side. What number do you think, what angle do you think goes here? 90 degrees. Okay, we're breaking it down that if I were to have an initial arm here and a terminal arm straight up, that has to make a 90-degree angle. What does this one have to be? Okay, and I bet you we can figure out this last one? 270. We're basically breaking it up, 360 divided by 4. Okay, as we move forward, you could see an angle at any one of these quadrants, and they're going to be broken up into those sections. Okay, an example might be, let's say I tell you, find me the angle of 230 degrees. Do I need to know exactly where 230 degrees is? No, but I know what quadrant should it be at. Has to be in 3. So, you know, if Jared decides to write at 230 degrees, it's approximately here. Really, I'm just looking at what key point? The quadrant. Making sure that he's at quadrant 3 and he's not at quadrant 2, saying that that's 222 degrees. That make sense? Okay? Huh? Are you good? Alright. So I just wanted to make that point out that we are breaking it up into 4 groups. Alright. So now I want you to try these. So these, you pick one that I'll do and I'll show you the rest. And I'll let you guys do the rest. So which one do you want me to do? The first, second, or third?
Third.
17 degrees? Okay. Sketch the rotation angle in standard position and state the quadrant in which the angle terminates. Rotational angle, basically just tell me where these angles are, and I want you to draw it in standard position. So if I'm doing 17 degrees, where's my initial arm always go? Always starts at the hinge at 0, 0 and goes across the x-axis. 17 degrees is between which quadrant? 0 to 90, 90 to 180, 180 to 270, or 270 to 360. 0 to 90. Is it closer to 0 or is it closer to 90? Closer to 0. I'm not going to take out a protractor and judge you based on the fact that you write it here or if you write it a little bit higher, a little bit lower. But know that this is 17 degrees and it's in quad 1. Sketch it in standard position and state the quadrant in which the angle terminates. Terminates, basically, that's why it's called a terminal arm. Terminates when finishes at 17 degrees, which is at quadrant 1. Pretty straightforward. I want you to do the other 2. Like I said, you do not need to take a protractor out and physically draw it out, but I want you to be cognizant of which quadrant it goes into. So this is where, if you don't have your marker or a pen or a sheet, I would find one instead of just looking and see where it's at. Yes, Jared? In 1 second, let me